So in this video, I'd like to talk about the relationship between gas laws and just show how they can be applied, give examples of how they can be applied to common stoichiometry problems. All right, so let's start with this question right here. What volume of oxygen at this pressure and this temperature would be required to make 945 grams of magnesium oxide when magnesium reacts with oxygen gas? All right, so there's a couple things here, and all of these things are things that we've done in this class. It's just a matter of combining them to solve a problem. All right, so first of all, what reaction are we talking about? All right, we can use the words here. We're making magnesium oxide by letting magnesium react with oxygen gas. All right, so what this involves would be, let's start off with just the words. All right. Magnesium plus, what are we combining that? It's going to react with oxygen gas. And it's going to make magnesium oxide. All right, so I do want to point out, I would encourage you to take a look at this problem and see if you can figure out a way to solve it, before watching this. All right. I think it's much more value if you can figure out the parts of it that you need help with than simply just to watch the solution. All right. Okay. So what we would typically do here is we would want to see this as a formula equation. All right, and then we're going to want to balance that. So the formula for magnesium is Mg. All right, for oxygen, remember that's one of those Brinkelhoff elements, O2, and it's going to make magnesium oxide. All right, and remember magnesium oxide, that's an ionic compound. So to get its formula, we're going to crisscross these two things, and you eventually will get to MgO, because that will simplify down to a 1-to-1 ratio. All right, we want to balance this. So to balance this, we need 2 of these, we need 2 of these right here, and we now need to go back to the question. All right, so how much would be required to make 945 grams of this stuff right here? So the chemicals that we're dealing with here are magnesium oxide and oxygen. All right, so we want to figure out, how do we go from 945 grams of this stuff to get to a certain volume, certain number of liters of that thing right there. All right, so a general plan. All right, what could we get to? So what do we need in order to calculate a volume based on this? Well, from our gas laws, we have that that relationship, PV equals nRT. All right, so we know the pressure that's given in the problem. It's asking us for the volume. All right, what about this? N, that is moles. All right, moles can be figured out from stoichiometry. All right, we have R. All right, that is something, since we know that this is done in atmospheres, we know the units that will go into that. So we know that, and we also know the temperature. All right, and remember in this right here, we're going to want to convert that to Kelvin. So that's going to be 298 Kelvin. All right. So so how do we figure out? So we know, once we know the number of moles of oxygen gas, which we can figure out from stoichiometry, we have everything that we need in order to solve this problem. All right. So how do we get from 900? So could we get from 945 grams of magnesium oxide of this thing to a certain number of moles of oxygen gas. All right, and we can do that just with common stoichiometry. All right, so we're going to start the problem off with what the problem gives us. All right, and we're going to try, we're just going to do standard stoichiometry. All right, the first thing that we would do is we could say that 1 mole of magnesium oxide is going to correspond to a certain number of grams of magnesium oxide. Okay, that would, so we have 1 mole of magnesium oxide is going to be 40.30 grams of magnesium oxide. And then we can figure out by the mole-to-mole ratio how many moles of oxygen would be required. All right, so we're just going to say that for every 2 moles of MgO, that should require 1 mole of oxygen. All right, and again, that just comes from the mole ratio that we can see in the balanced equation. All right, so if we solve this particular crossbar right here, we now can figure out that will tell us the number of moles of oxygen. All right, and that's going to work out to 11.7 moles of oxygen. All right, so this, remember what in our gas laws, that's what N is. All right, N is number of moles of gas. All right, so what we did here is we solved for our N. All right, so we now have a problem where all we have to do is, it's essentially like a gas loss problem. All right, what volume would you of the oxygen would you have if you had this many moles of it at this pressure and this temperature? All right, and we can solve that just by using the ideal gas law. All right, PV equals nRT. All right, so the thing that we don't know is the volume. So let's do a little algebra. PV equals nRT. Let's get the volume by itself. All right, equals nRT over P. And we're going to plug into that. We're going to plug into that the values. All right, our N is going to be the number of moles. All right, our R can be one of 3 values. And we can see here that the pressure is given in atmospheres. So I'm going to want to use that value that expresses it in atmospheres. So that's going to be, let me see here. That's going to be, oops, sorry. So that's going to be this particular version of it right here. All right, so that is the R value. We're then going to plug our temperature in. Our temperature is given in the problem. Remember that it's got to be in Kelvin, so that's going to be 298 Kelvin. And then you're going to divide that by the pressure. All right, and the pressure is also given in the problem, 0.962 atmospheres. All right, we would then plug those numbers into our calculator, and that would give us our final answer. Here's what the final answer would be. And again, remember you would have to round it to 3 significant figures, because if you look at the values that go into the calculation, that's how many would be there. So one more example. After the combustion of this chemical, we collect 0.42 liters of carbon dioxide gas at standard temperature and pressure. All right. Okay. So I'm just going to adjust this question a little bit to make it something that would involve requiring a gas law. All right. So instead of standard temperature and pressure, we're going to say that it's collected at this pressure and this temperature right here. All right, how many grams of this were combusted? All right, so first of all, we can use this information right here to calculate the number of, so in stoichiometry, if we have a way to get to moles, we can solve the problem. Okay, so taking that, that information, we can plug it into the ideal gas equation, and we can end up solving for the number of moles. Okay, and so we can figure out from the ideal gas equation that we would have this number of moles of carbon dioxide. All right, notice that I've rounded it to two significant figures, and the reason for that is if you look at the number of significant figures in the numbers going in, that would be the thing with the fewest number of sig figs. All right, so at this point, you might as well just say in the problem that how many grams of this wood right here would be combusted if we collected this many moles of carbon dioxide. All right, so at this point, it's just a standard stoichiometry problem. All right, so let's start with the balanced equation. Okay, and so we have this balanced equation. And so essentially this problem would be how many grams of C2H6 would have been combusted if we collected this many moles of this chemical right here. So it just comes down to a standard crossbar equation. All right, so let's start the crossbar with what we know. And then see if we can work backwards. All right, well, we know a mole ratio between carbon dioxide and this material right here. So for every 4 moles of CO2 that's created, that would have come from 2 moles of C2H6. And the question is asking for how many grams of that would be combusted. So we can create a relationship for every 1 mole of C2H6. How many grams of C2H6? And that's just going to correspond to the molar mass of this particular chemical right here. And that's going to be 30.07 grams of that. All right, so plugging these into our calculator. All right, and so solving for that particular crossbar, we can see that we would get this number of grams of ethane, or sorry, C2H6.